In this section, we're going to look at chemical equations. We've already looked at chemical formulas. For example, sodium chloride is NaCl, water is H2O, hydrogen peroxide is H2O2. Now we're going to look at chemical equations, which is really how we represent change in chemistry. And so a chemical equation uses the symbols that we've talked about and the chemical formulas we've used, but to discuss change. In physics, we might be interested in how far we can throw a ball. That ball is changing its position in time. In biology, we might be interested in how fast cells divide, or how much material is produced in a crop. That's change that's occurring. And so that's implicit in chemistry, our study of chemistry as well, is that in chemistry we want to predict how much material we're going to make, how fast it's going to be made, how slow it's going to be made, how efficient it's going to be made. But implicit in that is the idea of change. Science allows us to predict the future, and that's what we're trying to do. So first we try to interpret and write chemical equations, and then we'll look at what's called balancing, mass balance by inspection. So let's begin with this first equation here that's written, NH3 plus HCl, and then you see an arrow pointing toward NH4Cl. The substances that the arrow is pointing away from are called reactants. So NH3 is a reactant, HCl is a reactant. The plus sign is written there to indicate that these are separate materials. So NH3 is a different material from HCl. We have to add those two things together. If you were going to bake a cake, we might say flour plus sugar plus eggs plus baking soda plus vanilla. The plus signs indicate that there are different substances. The arrow points toward the product. That's the substance that we either want to make, or maybe we don't want to make it, but we're concerned it's going to be made. In any case, we predict it's going to be made. So this equation shows us that NH3 will react with HCl to produce NH4Cl. And that is a prediction. It's predicting the production of NH4Cl, which, by the way, is called ammonium chloride. NH3 is called ammonia. HCl is called hydrogen chloride. So ammonia plus hydrogen chloride produce NH4Cl. There's a temporal aspect of this. We would expect that before the reaction begins, we would have NH3 and HCl. After the reaction is done, we would have NH4Cl. Here's the second one. CaCO3 turns into or produces CaO plus CO2. The reactant, the substance the arrow points away from, is typically written on the left side, but not always. CaCO3, calcium carbonate, is the reactant. It is producing, the arrow points toward the product, CaO plus CO2, calcium oxide and carbon dioxide. This is, by the way, called a decomposition reaction. Calcium carbonate is decomposing into calcium oxide and carbon dioxide, breaking up into. That is in a change we're discussing. The third one here, S plus O2 forms or produces or makes SO2, sulfur, an element, plus oxygen, an element, forming a compound, sulfur dioxide. That's a reaction. Here's another one, SO3 plus H2O forming H2SO4. Sulfur trioxide plus water forms sulfuric acid, the reactants and the products. A couple more. Now, one thing to talk about is states of matter. We also will often indicate the states of matter. Substances can exist as gases, they can exist as liquids, and they can exist as solids. And whether something is a solid, liquid, or gas can be important in a reaction, usually is. So we often indicate the state of matter as well. Not always, but most of the time. So ammonia, in this particular reaction, has a G written next to it in parentheses. That means it's a gas. HCl, a G, that means it's a gas. NH4Cl, S, that means it's a solid. So Substances, we're indicating what state of matter they're in, solid, liquid, or gas, or a substance dissolved in water. So look at the last one on the right, SO3 gas plus H2O liquid. What's happening is the sulfur trioxide, is dissolving into the water, but reacting with the water to form H2SO4, aqueous. Aqueous means dissolved in water. Sugar dissolves in water. Salt dissolves in water, so we write them as aqueous, AQ for short. The next thing we often do is we balance chemical equations. So the first balancing of chemical equations is shown here as the reaction of potassium chlorate, KClO3, which is a solid, being heated. That little triangle written above the arrow is heating symbol. That means we're heating it, putting a flame to it to heat it. It is decomposing into KCl, potassium chloride, which is a solid, so it's not high enough to melt it, but also a gas, O2. And here we've balanced the equation. Now here's the balancing aspect of this. This is sort of the second part of our discussion here. We often are interested in amounts of materials. If we are interested in amounts of materials, for example, how much of something is going to be made, how much of something reacts, we then balance the equation. This is essentially mass conservation. A chemical reaction cannot turn 2 potassium atoms into 1 potassium atom, or 3 oxygens into 6 oxygens. Chemical reactions don't work that way. If the reactants have 5 atoms of an element, 5 sodiums, for example, the products also have to have 5 sodiums. So mathematically, the way we deal with that is through balancing. So notice that there's a 2 in front of the KClO3. That means there's 2 potassiums, 2 chlorines, and 6 oxygens. Not 2 oxygens, but 6, because the 2 is the number of KClO3s, but each KClO3 has 3 oxygens. So if you have 2 and 3, 2 times 3, you would have 6 oxygens. On the right side of the equation, after the arrow, there's also a 2 in front of the KCl. Why? 2 potassiums, 2 chlorines. Notice that the 2 in front of the KCl ensures that we have the same number of potassiums and chlorines on both sides. But what about the oxygen? On the left side, we have 6 oxygens, so we got to have 6 on the right. So the way we deal with that is we put a 3 in front of the O2. 3 times 2 is 6. So now we have what's called a balanced equation. Some equations are really simple to balance, others are hard. There are probably a dozen types of ways, or a dozen ways to balance equations. We're only going to show you one in here. It's called inspection. So let's take a look at the first example showing you how to do it. 2H2, 2 hydrogen molecules in gaseous form, reacting with 1 oxygen molecule in gaseous form to form 2 liquid waters. Notice the balanced equation there. Why is it balanced in such a way? Well, O2 cannot be changed to O in this equation. So there are 2 oxygens. And water has H2O is the formula. 2 hydrogens, 1 oxygen. Those can't be changed. We can't change O2 into O. We can't change H2O into HO. So we have to keep those formulas the same. So to ensure that we have 2 oxygens on the right side, we have to have 2 waters. And to ensure now that we have 4 hydrogens on the left side, we have to have 2 hydrogens. So we'll go through the inspection on this in a moment, but the point is, if we have O2 and we can't change that into O, then the O2 is going to get converted into 2 waters. And because you have 2 waters, that means we're going to need 2 hydrogens to ensure that it's balanced. Notice that on the left side of the balanced equation, there's 4 hydrogens and 2 oxygens, and on the right side of the equation, there's 4 hydrogens and 2 oxygens. It's a balanced equation. There is no requirement that gases be the same on both sides, but there is a requirement that the number of atoms of each element is the same. So here's a method on page 89 showing you how to do it. We're going to look at a specific type of balanced equation, which is called combustion. Combustion is important, very, very important, so we're going to use that as our example. So here's the first one we're going to look at. C4H10 gas plus O2 gas forms CO2 gas plus H2O liquid. So there's the equation, but it's not balanced. How do we know it's not balanced? There's 4 carbons in butane, 4 on the left side, but there's only 1 carbon in carbon dioxide, 1 on the right side. That's not balanced. That right there tells us it's not balanced. So here's what we're going to do. For combustion, combustion is typically C something H something plus O2 to produce CO2 plus H2O. And that is something you would probably want to memorize. Combustion, C something H something plus O2 gives you CO2 plus H2O. That's a good thing to remember. So here's how we're going to do it. We're going to do each element separately, and we're going to go in a particular order. We're going to do carbon first, then hydrogen, then oxygen. CHO, that's the general method for doing combustion. So let's begin with the carbon. There are 4 carbons on the left, 1 on the right. So there's more carbons on the left than there are on the right. So we need to have more on the right. So since we have 1 on the right side, 1 carbon, putting in 4 in front of it gives us 4 carbons, and that would be the same as the one on the left. So multiply CO2 by 4. That now gives us 4 carbons. So the second line here, you'll see it's C4H10 plus O2 gives you 4 CO2 plus H2O. That's what they're doing there. They're balancing carbon first. Then we're going to do hydrogen. So in the third step, or the third line, I should say, the third equation that's written here, we notice that there's 10 hydrogens on the left, but only 2 on the right, so we write a 5 in front of the water. Why? Because there's fewer hydrogens on the right than there are on the left, so we need to have more hydrogens on the right, so we write a 5. Where's 5 coming from? 5 times 2 is 10. 5 H2Os gives us 10 hydrogens on the right. Now that we have 10 on both sides, hydrogen is balanced. Then we go to oxygen. Now, oxygen's trickier in some cases. We're going to have to use fractions sometimes. Not always, but sometimes. So here's how we go about the oxygens. After we add the 5 in front of the water, we're going to count up the number of oxygens on both sides. On the left side, it's 2. On the right side, it's 8 plus 5, which is 13. 4 times 2 is 8, plus 5 times 1 is 5. 8 plus 5 is 13. There's only 2 on the left. There's fewer on the left now, so we need to multiply the O2 by something to get it up to 13. So what do you multiply 2 by to get 13? Something times 2 equals 13. Well, use your algebra. X times 2 equals 13. Divide both sides by 2. X would be 13 over 2. So notice on the fourth line, there's your 13 over 2. In my opinion, you're done. That's the balanced equation. C4H10 plus 13 halves O2 to form 4 CO2 plus 5 H2O. A little thing about general chemistry is that some things are done for not necessarily good reasons. I would say that third step is it. We've got the same number of atoms on both sides. We're done. Most textbooks will then ask you to do a next step, to do a fourth step. And so I would suggest you do that fourth step, particularly when you're doing ALEKS problems. The idea is that it is often the case that we do not want to have fractions in a balanced equation. I'm not arguing that's true. I think it's perfectly fine to have a fraction in a balanced equation, but we'll follow their procedure here. To get rid of the fraction, you multiply by 2. And the reason for that is that if you have 1/2 and you multiply it by 2, that gives you 1. If you have 3 halves and you multiply that by 2, that gives you 3. You now have whole numbers. If you balance one substance, if you multiply one substance by 2, to keep it balanced, you got to multiply everything in the equation by 2. So if we multiply 13 halves by 2, that gives us 13, but we also have to multiply the C4H10 by 2 and the CO2 by 2 and the H2O by 2. So we multiply everything by 2. That gives us whole numbers, 2C4H10 gas plus 13O2 gas forms 8CO2 gas plus 10 H2O liquid. Balanced equation. There's a little check here, 8 carbons on both sides, 20 hydrogens on both sides, 26 oxygens on both sides. Balanced equation. Okay? Practice, practice, practice. Here's an example. Write and balance the chemical equation for the aqueous reaction of barium hydroxide and perchloric acid to form aqueous barium perchlorate and water. I would be surprised if you very easily wrote this out and got all the formulas right. In chapter 2, there's practice learning how to name compounds and write their formulas. It's not an easy thing. It takes time to get good at it. So for this one, I'm just going to put us all the way down to the solution where we get to the first step. Barium hydroxide, that one you probably should be able to write out. Barium is in the second column, so it's +2. Hydroxide has a charge of -1, so we need 2 hydroxides for every barium to balance the charge. Remember, 2 times -1 would be the opposite of +2. So BaOH2, it does say it's aqueous, so we write AQ, plus perchloric acid. You may not know what perchloric acid is, quite frankly. Perchloric acid is HClO4. So write that down, HClO4 aqueous. The products are barium perchlorate. That one's not an obvious thing to write, but if you practice the naming from chapter 2, you'll be able to get it. BaClO4 aqueous plus, and then of course liquid water, that's not a problem. If it says water, but it doesn't give the state of matter, assume it's liquid. So there's our chemical formula. There's different ways to balance this. Now, the method they suggest in here is to treat the perchlorate, ClO4 minus, as a unit and balance it as specific units. So instead of doing chlorine and oxygen separately, do the perchlorate together. I think that's a good idea with polyatomic ions. So if you have a chemical equation that has SO4, balance the SO4 together, the polyatomic ions. The list of the polyatomic ions is given in chapter 2. So let's do the perchlorate together. First, I'm going to start with the barium. There's 1 barium on both sides. That's already done. Don't worry about barium. Next thing is hydroxide, OH. Well, there's a hydroxide on the left, but there's not a hydroxide on the right. So let's skip it. Let's go over to the next one. Yeah, there's a hydrogen on the HClO4, but there's a hydrogen in 3 different substances. That's complicated. But if you recognize the polyatomic ion, ClO4, you'll notice there's 1 ClO4 on the left, but 2 on the right. ClO4 2. So put a 2 in front of the HClO4. If you do that, now the ClO4 will be balanced. Okay? So let's take a look. I'm going to come down here to the bottom step here. There's a 2 in front of the HClO4, so that balances that. Now what you can do is you can say, well, wait a minute, ClO4 has oxygen, so the oxygen can get balanced partially through that. We just have to check on the hydrogens. So what I'm going to do is I'm going to count the number of hydrogens on the left, 2 hydrogens on the left for the BaOH2, and 2 on the second substance, HClO4, because there's 2 of them. So that's 4 hydrogens. On the product side, there's no hydrogens in the barium perchlorate, but there's water. Water has 2. So if you put a 2 in front of the water, that gives you 4 hydrogens. So now you got 4 hydrogens on both sides, and now you've got a balanced equation. So the final balanced equation is BaOH2 plus 2HClO4 gives you BaClO4 plus 2H2O. Now you got it balanced. You can check each element if you want, and then you got it balanced. Okay. So try the practice problems. The practice problem C, just to point that one out, again, our color coding, black is carbon, white is hydrogen. This one's getting kind of tricky. How do you count those hydrogens in there on that first substance? It looks to me as though it's got 5 carbons. 1, 2, 3, 4, 5. They're going up, down, up, down. So there's 5. The number of hydrogens, they are hard to see, but it looks like it's got 3, 2, 2, 2, 3. So 3 plus 2 plus 2 plus 2 plus 3. So that's 6 plus 6. Looks like it's 12. So it looks like it's C5H12 plus O2 gives you CO2 plus H2O. That's combustion. You can balance that one. C5H12 plus O2 gives you CO2 plus H2O. Okay. Here's another one. This is an example of butyric acid. My understanding is butyric acid doesn't smell very good. I've heard that before. I'm not sure, though. I've never smelled it. In any case, this is an example where they want you to go through metabolism. For those of you that are biology or healthcare majors, metabolism in this case, the way we use that term in chemistry is we mean combustion. Because when we metabolize things, often the final product is carbon dioxide and water reacting with oxygen. So that's the same equation as combustion. So when you go through this one, you're going to go through a combustion problem. Okay? C something, H something, O something plus O2 gives you CO2 and H2O. Balancing equations can be simple for you. It can be hard. So go through as many of these problems as you can. And if you need help with them, let me know. I can help you out on balancing. It's really just practice, practice, practice.